Hello, everybody. I'm very glad to be here at the conference. For a long time I haven't been in conferences, and it's good to be around this group. It seems so far really interesting. So, well, this paper we are presenting with the group, Brussels group, led by Diederik Aerts, the new student, Linette Bertrand, Maximiliano, Sandro, and me. Maximiliano is not known. He was in IQSA this year. It's a guy that is joining us. Okay, so I will present something that is kind of like the new stuff we have been working on the last years. Okay, so the first slide is just for those who don't know, like the quantum cognition, are not so familiar with it. So it's like this is the idea of the field: identify quantum structure and develop quantum-like modeling in cognitive science or other areas. And what do we mean by quantum structure? Either incompatible measurements or state superposition, identify interference or entanglement. It's our other contextuality could be added to the list as an important word as well. And then by quantum models, I just mentioned places where this have been worked on, so categorization in psychology, or like for words and word association, like those. Other people have worked in decision making or psychological experiments in general, like gambles and stuff. Other people are working currently in information retrieval or natural language processing. At this conference is where we find like all these advances. And regarding like what we do, like in our group, we don't take a position with respect to the brain or microtubules, which is very interesting. I didn't know about it, so. But still, I cannot say that this is compatible with this microtubules view of the brain, not at this moment. So I will just stick to the standard view of how do we approach quantum cognition, which is we work with data, not with the architecture that builds the data. Just for now. Okay, so what are to be a little bit more precise as a overview of the features that are used to develop quantum models are the non-commuting operators. So we were just talking about this now, like question order effects, and the way they are modeled is using like incompatible or non-commuting operators. Similarly, the superposition interference, it's just like applying the Born rule to this superposition state, and then you get the interference in the third term, you see here. And this is like the one that you use to model either super-additive or sub-additive probabilities. And the typical example is the Guppy effect, and also the conjunction fallacy in psychology. And entanglement, maybe not so popularly used, but still it's another important feature of quantum systems that some states are known separately, and then you can use it to model semantic dependencies, maybe in lexicon or for concepts, or either as proposed by some people in Italy in music, like perception of music as well could be modeled. I don't know if someone is going to talk about that later. And okay, just to finish the overview, this has become in a way popular in science. Some people are working on that, and there are many articles and many like special issues, and there is also a lot of production. I think I'm talking to the people who are doing this, so, but I didn't know the audience in advance. Now we go to the problem that motivates this talk, which is that there are two problems. One is that there are two cognitive phenomena that are like proven. One of them is called response replicability, which like answers given by response become deterministic once known. So if I say yes, I will probably, regardless of what happens in between in the experiment, if you ask again the same question, I will say yes again. And this is modeled usually assuming that operators are first-kind measurements. So then the projection leads you within the subspace, and then the answer is going to be always positive, or it's gonna, the state is gonna belong to the subspace where it is projected after as well. So that's why it's a projector, this measurement. So then, by assuming the Born rule, basically using first kind measurement, you will have response replicability. But the problem is that if you connect this with the question order effect that has been already explained. So if I provide questions in different orders, then I don't get the same probabilities. So we use this saying, okay, these observables are incompatible, so the operators are non-commutable. And then the problem is that if you observe these two effects together, you cannot model it using the Hilbert space approach using the operators. Why? Because question order effect implies non-commutative observables or operators, and response replicability imply commutative operators. So then you get this contradiction, and then you say, how do we cope with this basic problem? Response replicability is the fact that we are consistent and have memory, and question order is contextuality. So how do we handle these two problems together? And then we propose that cognitive models beyond Hilbert space are needed. And then, this is the outline of the talk. We will discuss the nature of the cognitive entity from this quantum foundational perspective. So it's like the quantum cognition, typical foundational approach. Then we provide an abstract formal model for the cognitive entity, which probably some of you are familiar with already, and then describe this general tension reduction model, which is a little bit, it's a probabilistic machine, basically, that realizes or like represents this formal abstract cognitive entity. And then we show how these two problems that were not compatible using the Hilbert space formulation become compatible in this model. And we show, like, very quickly how to model conflictive, the data that has been conflicted with these problems. And then leaving some space for discussion, hopefully. Okay. So in the Brussels approach, which is the group that I work with, these are the typical assumptions we introduce when trying to make models of a cognitive entity in a psychological experiment. We assume the existence of a conceptual reality, something that is ontologically independent from the subjective beliefs of a participant. So we assume that there is an out there, a conceptual out there, to be modeled, to be described. And then the participants, in an experiment, we are saying this is the context of the discussion, a psychological experiment. A participant acts as a measurement context that interacts with this element of conceptual reality in a non-predictable way, in an indeterministic way. And so we seek for an operational and realistic model of a cognitive entity. Operational in the sense that what happens in the psychological experiment is described in terms of operations within the formalism, and realistic in the sense that we assume the existence of a conceptual reality that is to be described. So the cognitive entity related to the question or the psychological experiment is prepared in a lab. It's prepared in a state that we call PS. P stands for state in the usual notation we use, and the S is okay. And then the participant, we assume a number n of participants in an experiment responding to question A, like a dichotomic either yes or no, is going to be represented by a context that induces a state transition from the preparation state to one of the outcome states. Okay, so this little notation here, introduced just to simplify the talk. So you get the initial state, you get the context, and then you get the outcome state, X, which can be yes or no for this dichotomic measurement. And then you can collect the frequency, the large number, if this n is large, you can make relative frequencies and calculate or obtain experimental transition probabilities from the initial state to the outcome state, and this is where you have your statistics and you make your models. These models with the idea to represent these probabilities. So, what I'm saying, what I was explaining before, is just like the basic background of this state context property formalism that has been developed initially by the people that were in like lattice theoretical approach to quantum theory, and then it was modified a little bit, adding the properties actually, to model also cognitive entities. But we always, at this talk, and most of the time, we just remain with state and contexts. Introducing properties on top of that, it's a little bit hard from an experimental perspective to have a model where you can handle all these variables. Generally, we just work with state and contexts. Okay, so that's the idea. We start with this modeling, and then, as I just said, the probabilities are built in this way. So you get the probability of outcome X, AX is going to be built as the probability of the transition from state PS, given the context EA, to the outcome state AX, and it is calculated by the number of cases within these n participants that make such transition. Of course, this works not just for one measurement, but for multiple measurements. So we go back to this classical example, paradigmatic, of Clinton and Gore honesty. And this is how you can solve, using this abstract formalism, the question order effect. Because if you see, there are the probability of getting some answer for question B and some answer for question A is given by a formula that is built up on the same idea. So, for example, in this case, if you ask B and then A, you start from state S, which is the preparation state, and you go to the outcome B set, and then from B set you go to the outcome AX. While if you ask the questions in reverse order, you start from S and go to A, and then from A go to B. And this is why you can basically, the model is trivially able to describe question orders, because they are actually described differently. What is asked first and second is described differently. So this is why it's not a big deal to model question order effects in this framework. But now, of course, anybody could put like many parameters and say this is that, and then make a big formula with enough parameters so everything can fit. But the idea is to create some sort of more constrained system where you can still recover this type of behavior. So this is what the general tension reduction model is about. So creating some probabilistic machine that describes what we just did before. So this is the idea. Some of you might be familiar, and there is a movie. If we have time, I can show you the movie that is on YouTube on how this works. Maybe I'll show it if there is time. So the idea is the following. The state of the system, this is very similar to the block sphere, when you make a block sphere to show like a qubit in a block sphere. This is very similar. There are some differences, but I won't discuss in this talk. So the state of the system is a unitary vector, let's say, in this sphere, and the measurement is an elastic band that is attached to two antipodal extremes of the sphere. Okay? So the process of measurement is as follows. You got the state, and then the state sort of folds over this elastic band, and this elastic can break. You can define the distribution of breakability of the elastic or however you want, but it breaks at some point, and then it delivers an outcome. Because if it breaks, as in this case, if it breaks to the left of where the point fell, then the point is going to attach to the outcome to the right. If the elastic will have broken in the other side, then you will get the different outcome. So this very simple probabilistic machine can produce quantum probabilities, I will show in the next slide. And in the context of cognition, so this is the idea that this probabilistic machine actually is able to, or is not so hard to interpret. What is it about? So A is going to be the state preparation, so the way the point is there and the way the elastic band is set, so the geometry of these two elements, which is basically this angle in this simple case, it's representing the state preparation. Then the B which is when the point falls over the elastic, is when this is a very hand-waving concept, semantic tensions. The semantic tensions of the situation to be described gets in an equilibrium state, which is unstable equilibrium because you still have to answer. So you know there are two answers for the question. Do you like this? Yes, no. And then right before responding, you are in a tension state that has to be broken so you can respond. And this is a spontaneous process. It's non-deterministic in the way we describe. We say there is a probability distribution for breakability, but we cannot decide or know in advance where it is going to break. So then the point C is a spontaneous breaking of the symmetry of these tensions, where where the outcome is produced and delivered. So this probabilistic machine is our model of how people think in a psychological experiment, basically. That's the whole point, or what would be a conscious act or emotion named in the talk before, in the talk of the microtubulus talk. Okay, so why you can recover quantum probabilities if you just do the geometry analyze here. You get the angle theta, and then the elastic band is of length 2. You calculate that you do the trigonometry here, and then you retrieve these probabilities, which are like the quantum probabilities for a two outcome measurement. Okay, so but it's important. Well, I will mention this now. You can get the quantum probabilities, but there are many more interesting facts about this probabilistic machine, which are all discussed in this paper, which is, I'm assuming that the elastic can break uniformly and this is not necessarily true. For example, I can just define a breakability region here and then leave the other points as unbreakable. This will be like just pieces of wood stacking the elastic. First of all, it's important to see that this is a first-kind measurement model, because once the elastic breaks, if you put the same elastic, it doesn't matter where the elastic is going to break, you will get the same outcome. You see, like, if the point gets stuck here and I reproduce a new elastic, it doesn't matter where it's going to break, I will also stay in the same outcome. So it's a first-kind measurements model. Second, which is something that I just said, if the elastic band can break uniformly, you get quantum probability. If the elastic band, instead, only can break in the center, like a Dirac delta function, then it becomes a classical probabilistic machine. And of course, anything in between, like this case where you have breakability region, is neither quantum, neither classical. So it's something strange, or in between, non-classified, to be classified. And then you can generalize this model, because the elastic sound really like boring or like trivial, but you can generalize to a sphere to an hypersphere of any dimension you want, and the elastic is not an elastic, it turns into a hypermembrane that can be broken, and then you can model degenerate measurements or measurements with multiple outcomes. And the geometry of this is, once you think about it, is very beautiful. The movie that I might show also contains that. And another thing that I won't discuss here, but is that you can recover quantum probability as a universal average over all the possible ways in which the elastic can break. This is a very interesting thing because it helps to connect the modeling of single people with the modeling of at the statistical level. I don't know if there's going to be time for that, because also the talk is not about that. But the bottom line of this is that the GTR allows to model different ways of choosing from people, the different ways in which people choose to decide something in the raw structure. Raw is the breakability distribution. So you can model how, like a quantum way, a classical way, or something in between. You can have very different ways of choosing the way you answer in this model. So, and not in the state of the cognitive entity, it's in the measurement where you put this, what normally is called like the subjectivity of people, which is put in the state, we put it in the measurement, and this raw structure. Okay. So, just to go with to the modeling of data, these paradigmatic experiments, the Clinton-Gore and also the Rose-Jackson, which is the same. It's, instead of asking who's going to be president, you ask if whether or not they're going to go in the Hall of Fame. And then, depending on who you ask first, two sport guys, I think baseball players, basketball, I don't know, like two like sport stars. You see, you ask, you think this guy is going to go in the Hall of Fame or the other, and then you ask in different order. You get question order effects, and then you can not complicate. You can create a model starting from the outcome probabilities. You can create not just one. Actually, there is some freedom in the parameters to model this, but making some simplifying assumptions, you can get the representation of data in this form. So, but can we make this model compatible with response replicability, which was the question in the first place? The question order effect is one thing, the response replicability is another thing, the incompatibility of these things within the Hilbert space model is the question. We present this formalism, show that question order effects can be modeled, and now the last step is to show that this is completely compatible with the response replicability, which is somehow like the creation of memory and the will to be consistent with your memory. So, how to do this? You need to we need, or like the idea is to update the raw structure after measurement. So, in the same way, like you get the Luder's postulate that the state is renormalized within the subspace where it is projected after measurement, we also have now like a sort of Luder postulate for measurements. So once you perform the measurement, you can ensure response replicability regardless of how many questions are asked in between, while keeping the question order effects. So to make it simple, I will explain for one case. So consider the sequential questions A, B, and the outcomes we got are yes, yes. Okay. So this is how the elastic band gets updated. When you ask A, actually there is no update. No need to update. But when a new question is asked, then you see that the elastic band is stretched a little bit, and I will explain in a formula what is the actual formula. But the idea is that, as I said, these are first kind measurements, because when you fall into the outcome, then you put the same elastic and the answer is deterministic. And because you can modify the raw distribution here, you can modify the raw distribution in a way that the elastic, it doesn't matter where it breaks, you will always recover the outcome that was produced in the previous question. And in this case, what you have to do is just to create a zone of non-breakability, extend it a little bit. This is like the Clinton-Gore data model. So in order to make it compatible with response replicability, you just have to update the region of non-breakability, so the raw distribution. And then you get that the projections, because remember, like the state always falls. For example, if I'm in this state and I want to measure A, I will project down and then break the elastic. If I'm in this state, I will project down and break the elastic. So you ensure that the elastic cannot break to the wrong side. And with this, this probabilistic machine shows, I hope the point is clear. I don't know if it's clear, but you can ask me. With this trick, the probabilistic machine gets compatible and can model question order effects and response replicability. So to make it a little bit more formal, here are the 4 possible outcomes and the way that you have to update the raw distribution. So this is the characteristic function of the interval where you allow the elastic to be broken, and this is like the initial distribution, and this is the normalization constant. Because of course the region of breakability is smaller or larger, so it's adapted, then you have to normalize. So, okay, now it was presented, this abstract entity realized in a model, showing that these things are, you can make question order effects and response replicability compatible. But is that so? Is that it? Or you can continue and go further with other cognitive phenomena, which is the idea. Of course, we want to have some sort of framework that is compatible with any psychological phenomena we get confronted with. So then we thought, okay, let's try something different, like unpacking effects. And the idea of an unpacking effect, this is like the super influential research of Tversky and Kahneman as well. I think they come up with this the first. I don't know if they were the first, but they make it popular. So the unpacking effect is that you describe in equivalent things in different ways, and then you get different responses. So I will give an example. The winner of next US presidential election, this entity I will call W, okay? Because it's too long and then I have to fit it in the slide. So we'll call this W. When I say W, I mean that. So is W a non-democrat? Is W an independent or Republican rather than a Democrat? Clearly, A and A prime are equivalent. And then if W is a non-democrat, will W be an independent? Then this is another question. It's specifying A prime. So with this, you can model, you can check question order effects in the context of unpacking. Because non-democrat in the US politics, as far as I know, you can, if you are non-democrat, you can only be independent or Republican. You don't have a third choice. Independent is kind of like
the third most polling candidate now is a libertarian.
Ah, okay. Yeah, but in the newspaper is an independent candidate. No, now it exists formally as a new outcome. Nice. Yeah, I didn't know. Sorry. But by the time of this research, probably it didn't exist. So non-democrat, this being non-democrat or Republican is equivalent to being non-democrat, basically. But if you say independent or Republican, somehow people understand something different, act different. And you can test this and mix it with question order effects and so on. And the idea is that A is the packed description and A prime is the unpacked description, because you can unfold the possibilities in a disjunctive way. Yeah. Okay. So you can use the Hilbert formalism to model UP using incompatible measurements, but then you will get, again, the response replicability problem. And you could use it making also degenerate measurements, saying, okay, non-democrat is a degenerate measurement that have sub-measurements where you can identify whether you mean independent or Republican. But then you will have this, what is called, this, well, you will have this equality. You need to have that the sum of the sub-measurements will deliver the probability of the big measure, the non-sub measurement, the bigger measurement. Yeah. And this is a problem because this is not what you get from the data. The probability of an answer is not equal to the probability of the answers asking like the degenerate question after to sub-identifying. So you use, basically the data shows that A is not equal to A prime B for the outcome yes. So you get yes for this, and then yes, no, plus yes, yes, and they should be equal. The logic of the experiment is made that way, and you don't get the same probabilities. So this deviation, which has been observed in many other experiments as well, it's normal that people don't answer, like when you unfold questions, they don't answer the same way. And this can either be smaller or larger. So then you call it sub-additive probabilities or super additive probabilities. And yeah, this is a problem. But for the GTR model, you can also model this system, and it is explained in the paper how it goes. There is a little technicality here that the non-outcome of A and A prime is the same. So you have to collapse the elastic band having the same point for no in both questions represented on the sphere. So you gotta make it in a higher dimensional system. And this is geometrically a little bit complicated thing, but technically speaking, it is completely possible to model this using the GTR model. And this is what we plan to work next. And also all the other fallacies that have come, because the probabilistic machine, I think this, conclusion. This probabilistic machine is pretty strong. And I don't know if the discussion allows, or maybe for someone interested, I can explain more of this. So, conclusions. Question order effects and response replicability are put a challenge on Hilbert space-based quantum cognition. This is the fact. And then the GTR model is a probabilistic machine that generalizes classical and quantum probability and allows to model these things with no problem. The key of the probabilistic machine is that question order effects are modeled by assuming different, like the right elastic band orientation. So A means this and B means that. So if you move it a little bit, then you might change the probabilities. And then you can model the question order effects by putting the right elastic band orientation then. And the response replicability is solved by updating the respective elastic band distribution after the question is answered, which is like the act of memory. I'm going to remember this, so I just put this as a deterministic region in my conceptual representation, which is this sphere. And also it proposes an alternative to model other effects, such as unpacking effects, superadditive and subadditive probabilities. And for future research, we would like to go and also model the conjunction fallacy, because we have worked on this before and there are many models, so it's interesting to confront the model with this problem with multiple sequential measurements, not just A, B, B, A, putting C, D, E in between, and then see how the band distribution has to update, whether or not you will get some contradictions. Because I imagine that, I don't know this, but if you update the elastic band distribution and you have many, many measurements, maybe these updates will become incompatible. And I don't know, this could be tested experimentally. And the individual versus collective problem, which is very interesting. I know some other people who have worked on this, how to interpret the construction of probabilities. And in this model, the probabilistic machine can be used as a model for the individual mind. The mind is the measurement. Remember, the state is of this conceptual reality, and the mind is the measurement system in our formalism. It's the elastic band, basically. And the interesting fact is that if you have you integrate over all the possible ways of choosing, you recover quantum probability. So then the idea is that we might all be non-quantum probabilistic machines, but when we make a statistic out of us, it's very likely that we will get something like quantum. And this is, in a way, a justification of why quantum cognition has been successful so far in some things. We are not all quantum clones, but when we average over our behavior, then we will be equivalent to what a bunch of quantum clones will be. And this is what we want to explore using the GTR and making an explanation of this. Because also there are many I just show non-Hilbertian data. And this is because the sample of people is non-averaging properly, so you can retrieve the quantum probability. So for some large samples, for some experiments, we might get quantum probability, but when we don't get it, we still have an interpretation for that. And that's the generality of the thing. And all this, it's interesting that was proposed for the first time in 1997 in a very general way in a paper about this, because this was presented in the 80s and 90s as a way to show that quantum probabilities can be obtained in macroscopical systems in the very, very baby first steps of quantum interaction. And there is one paper that presented like how to obtain quantum probabilities in a survey using a very similar argument that what Acacio was showing, like the anti-correlations that are not possible to obtain in a classical system when you only can measure pairs of things and not the three things, and then like all what Abramsky has used as well. It's a very old argument from Borovev to show that certain statistical systems don't obey classical probability. And this was presented also Accardi has made proofs of this as well. And this was presented for the first time as a way to show that surveys might exhibit this behavior in 1997. And then it was proposed to develop something like interactive statistics. So a statistic that is generated with all these effects. And finally now we are like 20 years after the first idea, we are showing, like after the development of quantum cognition, that maybe this probabilistic machine is more useful than what was thought in the very beginning. So I invite everyone to read the paper and initiate a discussion, whatever you want. So thank you very much. The references for the paper.
So, questions? Yeah. On your diversity and Kahneman support paper, I guess it's called, the most dramatic result that they had was the earlier one, that in many cases, if you have a binary partition of events, then the probabilities add. But if you have a three-way or more than three-way, they do not. You showed it for three events. Can you actually show the more general thing, that why it is the case that generally, if you have two events, that the probabilities add, but not three?
The probabilities what?
Add.
And
If you have two, they add, and the basic paradigm is to take two, where they add, take one of the events of the two, and split it. So
Yeah.
now you have three, and now the total thing does not add. That's how the experiments were originally done and usually done.
yeah.
So what about the additivity of two? Why should binary things add, but three-ary things not add, according to your model?
Well, I do have the expression of the three outcome measurement.
Right.
I don't know if it's going to answer the fact that they don't add.
The two
So
ones should add, your three does not add.
yeah,
That's the effect. It violates probability.
yeah,
It's a partition, but the twos generally do add. That is the real problem that support theory tries to address.
mm. yeah,
Not that the three don't add, or Wolf-Owens don't add.
yeah. No, I don't think I have the answer like in the pocket. But I can, if you want, I can show you how it looks when you have three outcomes.
I saw that.
You have seen the video? Okay.
I saw how you can get it, yes.
Okay.
That's
Yeah. So no, but yeah, I will keep this question to be
And
addressed.
also, when you have three, generally, they add much more than one, not just a little bit, but quite a lot more.
Yeah.
Usually about 50% more. And very rarely do they ever add to less than one. That's a very rare event. It only happens in very special cases.
Yeah, well, before, like, not necessarily applying the GTR model, but just like doing a quantum model, you can define, okay, so let's say, well, you can say, okay, A is dichotomic, and then you can have a yes, a no, just to say, or A1, A2. A1, A2, and then 1 is split into two more. So this is going to be A11, A12, and A2. And then you get that the probabilities of this is 1, and then the probabilities of this is not 1, right? But you can, making like the typical quantum model that is done before, you can just say that there is an interference between, in this case, you can use an interference effect, I think, to create the systems in a way that when I will have to tell you more like in detail, but you can use normally when you have sub-additive or super-additive probabilities, you can use the typical superposition formula that I showed before, which is it's here.
Yes, the problem is not that you can't get it
Yes.
on probability. The problem is why in
Why?
the generic case, the everyday case, they add for 2, but not for 3. That generic case will not hold, I think, for your quantum probability. That is what the problem is. Somehow people are processing 2 in a very different way than processing 3.
Yeah.
That is the psychological puzzle. Why it should be the case.
Yeah. Well, let's discuss this later because it's gonna be a bit a mess for me to explain now what I think about it. But it is addressed in other work where we found some inequalities. Yeah, there is still time or
Yeah, we started
okay.
5
Just
minutes
like
so you got 2 quarter past.
one second. When you have one measurement with 2 possibilities, you get like let's say PA plus PA, P not A. Normally it's very close to 1. So this is, but then when you get, because I didn't work with 3, I worked with 4 then. AB plus P, A, not B, not AB plus P, not A, not B, plus the not of both. This is not equal to 1. And we did with various experiments. I don't really know the three atomic measurement. And we saw a clear deviation of this. Like it's not something that goes anywhere. It goes specifically in one part. And this can be explained to a large extent in this formula. Even eliminating the interference from the analysis, you can show that the tendency is to go to the average of the two probabilities when A and B, when you have A and B. So the 2 options, and then there is a superposition state between these 2 concepts. I don't know if you're familiar with it, that's why it can take longer. But then you create this average between the 2 probabilities, which has also been proposed as a way for the conjunction fallacy. People believe that there is an averaging process. But then you retrieve the averaging process from the operational model. And so, if when 2 concepts are combined, this is the point, you get that the average probability becomes the dominant probability instead of the minimum. If it's a conjunction, will be the minimum. And here you get the average. And when you get 2 numbers, the average is always in the middle. So this is why you get a super additive behavior as in general, like in the typical case. So I think this can be connected to what you said, but I'm not familiar with that.
Okay.
Sir.
Any other burning question? One down the
Sorry.
back.
Yeah.
In your first example, just one measurement, 2 possible outcomes. You calculate the probability, and it's a function of where it's not really a state vector, I guess, S, and where the elastic breaks.
Yeah.
And you define it in a 3-dimensional sphere. Why is it 3-dimensional? It's only, your whole system is only 2-dimensional.
Ah, okay. Yeah. So this.
Maybe I missed something, and I don't see why you need to.
No, because right after you work with 2 elastics,
Okay.
and then you
To
need a
continue
3rd dimension.
Okay.
Yeah. Yeah. But yeah, what you say, the state is here, and then the elastic is there,
You
and
don't have QI, you don't have the imaginary number.
yeah.
Just
The relative orientation between the state and the elastic is what defines the probability, and plus the elastic breakability distribution is what determines the probabilities.
Anything else? Okay, let's speak.